Contact-based manipulation, physically touching objects to interact with them, is the most common form of manipulation, but it's not the only one. For instance, humans commonly employ directed air to move or deform objects, which are primitives useful from cleaning the front yard to making glass art. Can robots acquire a similar manipulation skill? If so, there will be quite a few benefits. One of them is the ability to apply dense forces on the target object. It is in contrast with contact-based manipulation, which is restricted to applying force through sparse contacts. This attribute is particularly relevant when interacting with deformable objects, allowing for more control for these highly under-actuated objects. Air-based manipulation also allows us to manipulate objects beyond our physical reach range, such as those leaves in distance. And since air is much safer to move at high speeds than a robot, it can operate safely around people. In this work, we coin this capability DextAIRity, and we will study how to use it for deformable object manipulation, such as unfolding a crumpled cloth or opening a cloth bag. While cloth unfolding has been studied in many prior works, finding a fast and robust solution remains an unsolved problem. The majority of existing approaches use quasi-static actions such as pick and place. The strategy tends to be slow and often requires many interactions to achieve the goal. More recent lines of work have taken a dynamic action approach, using primitives such as flinging to interact with the cloth. This approach is generally more efficient. However, these actions are still restricted by a robot's reach range and the speed at which it can safely move. We found that when the cloth becomes large or heavy, this approach struggles to unfold the cloth. Instead, we adopted an air-based strategy and equipped our robot with a controllable commodity air pump. After learning a closed-loop policy for the pump, the robot can easily unfold a diverse array of clothing items, including this large dress, in seconds. Our system setup consists of 3 UR5 robot arms, 2 of which are equipped with parallel jaw grippers and 1 with an air pump. Visual observations are captured by a top-down camera. We take a learning-based approach to the problem. First, grasps are executed according to the grasping network. The cloth is then lifted and stretched taut in the middle of the workspace. Finally, blowing actions are executed using a closed-loop blowing policy. Here's another example of what this looks like in practice. In this particular case, because the shirt is relatively small, both Flingbot and our approach, DextAIRity, perform well. However, as clothing items become larger, contact-based flinging begins to suffer. Flingbot is only able to half unfold this large cloth, while our approach maintains good performance. And again, with an even larger cloth, we see the same story play out, where DextAIRity outperforms Flingbot. Here are more results. We found our approach exhibits strong generalization capability. While the policy was only trained with rectangular cloth examples, it is able to successfully generalize different shaped garments such as shirts and dresses. The second task we examined is opening a closed bag. While simple, opening a bag is an important prerequisite to the common downstream task of filling that bag with objects. Unlike in the cloth task, we assume that the closed bag has already been grasped by the robots. We again adopt a learning-based closed-loop approach using depth observations from a top-down camera. We found the simple task surprisingly difficult to accomplish with contact-based manipulation, even when using dynamic actions such as shaking the bag back and forth. We also explore implementing a heuristic fixed post-blowing policy, and while it performs slightly better, it also fails to reliably open the target bag. Conversely, our learning-based approach can quickly and reliably open the majority of bags we tested. Here's another example with a large plastic bag where DextAIRity opens the bag with only one trial. Here's an example of a smaller cotton bag. While the first blowing action is suboptimal, the robot is able to refine its action and open the bag in the following steps. Here are more results. Encouragingly, the blowing policy learned by our robot appears to generalize well over the diverse set of bags and random grasp positions. Our system is not without limitations. Here are a few typical failure modes. In case the corner of the fabric is rolled up by the air, reflecting some of those complex aerodynamic effects. Here the robot mistakenly grasped multiple layers of the fabric, preventing it to be fully unfolded. Finally, in this case, two layers of the bag stick together and prevent air ingress. This failure suggests an interesting direction of learning a coordinated policy that simultaneously adjusts three arms and combines the contact and air-based manipulation. For more details, please check out our paper. Thank you for watching.